Hi, AP Chem students. This is the class video for Tuesday, January 19th, 2021. So we get to enter the exciting world of energy and enthalpy and heat transfer and calorimetry. And this is Unit 6. So homework tonight is to watch the videos listed. These are AP Classroom videos, or to read the textbook pages. These are listed on Google Classroom, and to do the problems in the textbook that are listed right here. We also are planning to do a lab during class 2 on Thursday, so you should get the lab materials ready for lab 8. And if you take a look at lab 8, we're going to be measuring the heat of crystallization using reusable hand warmers, and these are the materials that you need from your lab kit. If you have any questions about where to find those things, let me know. So in this unit, chapter 5 mostly, we are going to tackle the subject of thermodynamics. So thermo meaning heat, dynamics meaning change, and so we're looking at how heat changes in a process, in a physical or chemical process. And really, Unit 6 is the first half of thermodynamics. The other kind of major part is entropy and the Gibbs free energy, and that will come up in Unit 9 after we do equilibrium. It'll make more sense that way, but we'll start kind of seeing some of those ideas in Unit 6 with heat. So energy is the capacity to do work, and heat is the energy that flows between two substances due to a difference in temperature. Work, we're not going to really talk about much at all in chemistry. Most of our processes are constant pressure, constant volume processes, and so work does not play a role. So chemistry focuses on heat. There's the two types of energy, kinetic and chemical potential. And so we have the energy of motion, and then we have the electrostatic attractions and repulsions in bonds and interactions like IMFs. So Unit 6 is going to focus on how thermal energy is transferred in physical and chemical processes. The SI unit for energy is the joule. So here is the joule, and you can see that this 1 kilogram meter squared per second those units can be found using the kinetic energy formula. Sometimes we'll use the calorie. The calorie is an older unit, but still in pretty wide use, especially because they are related to our food calorie. So the calorie is the amount of thermal energy required to raise the temperature of 1 gram of water by 1 degree Celsius or Kelvin. 1 degree Celsius in terms of change. So if you change the temperature of something by 1 degree Celsius, that is the same as changing the temperature of something by 1 Kelvin. They're exactly the same. So 1 calorie is equal to 4.184 joules, exactly. And it turns out that our food calorie is not a real calorie. It is actually a kcal. 1 food calorie is actually 1,000 calories. So when you eat a bag of Fritos here, you are actually taking in 160,000 real calories, because 160 here, 160, that's actually indicating kcalories. So one of the important parts of thinking about heat transfer and energy transfer is distinguishing the system from the surroundings. So systems are going to be the specific reaction or the object or the process that we are studying, okay? And then everything around that reaction is going to be the surroundings. So system basically, yeah, what we're interested in. And the surroundings are the rest. And if you put these two things together, the system and the surroundings, they equal the universe. Now, in chemistry, usually we are looking at a closed system where energy can exchange, but matter cannot, usually. So a reminder about what endothermic versus exothermic processes are. So an endothermic process is one that absorbs heat, and we'll use the letter Q to represent heat. Okay, so it absorbs heat from the surroundings. It has a positive sign, positive Q. Any endothermic reaction feels cold, like a cold pack, because it is absorbing energy from your hands. Your hands are part of the surroundings. An exothermic process is one that transfers or releases heat to the surroundings. So the sign of an exothermic process, the heat is negative. So exothermic, negative Q, endothermic, positive Q. And exothermic is negative Q, and it feels hot because heat is being released by the reaction. So for example, if you burn paper or you set off a hot pack, you feel heat being released, and your hands are the surroundings, so it feels that change, that increase in temperature. So here again, the representation of how heat is being absorbed or released in the system. And then we can relate this to delta H as well. Delta H is our heat of reaction again. We learned about that in kinetics. And delta H follows the same sign conventions as Q. So endothermic process, delta H is positive. Exothermic process, delta H is negative. Here are two potential energy diagrams again. So which of these is endothermic and which is exothermic? What are the signs of Q and delta H? So here's on the left is our exothermic reaction. We can see that the products are at a lower potential than the reactants. Okay, some energy has been released. Q, the heat, and delta H are negative. Oh, going back. Here on the right, we have an endothermic reaction, heat and negative, heat and delta H are positive. Here, the reactants have absorbed energy and the products are at a higher potential. So here's an example. We did these Paradex slides. People did them in breakout rooms together. And here we are burning coal, and we want to write a chemical equation representing the burning of coal. So coal is carbon, and we burn stuff with oxygen. So here we go. This is how we would represent this. Carbon plus oxygen goes to carbon dioxide plus energy being released. Okay? As we know, when we burn things, we release energy. So what we want to do is consider the amount of energy in the reactants compared to the products. Since we know that this is exothermic, right, the amount of energy in the reactant starts up here and then it goes down in energy. Okay, so we want to find the answer that shows that the reactants are higher in energy. That would be B. The reactant molecules have more potential energy. We convert those reactant molecules, we change their bond structure, their interactions, and then release them and release the energy and form the product molecules, which have less potential energy. So again, here, just a reminder of energy diagrams again. Here we have an exothermic reaction again. Here is another way to represent the exothermic reaction in a simpler way. Here we have an endothermic reaction. The products are higher in energy than the reactants. Again, here's a simple way to represent an endothermic reaction. This would apply to the reverse of the coal burning reaction if we turned carbon dioxide and took some energy and changed it back into coal and oxygen. All right, so again, make sure you know your sign conventions. Endothermic, positive Q, positive delta H. Exothermic, negative Q, negative delta H. Now we have an energy diagram here. Is this exothermic or endothermic? Well, we see that the products are lower in energy than the reactants, so this is exothermic. The reactants have released energy to form the products. Since this is exothermic, if I was near this reaction, I would feel hot. Okay, it's releasing heat. I would feel that heat. So now let's say that this energy diagram represents A plus B going to C plus D. Where should we put the energy? Well, again, this is exothermic, and the energy is being released, given off. Therefore, we should put the energy on the right because it is being produced. It's as if it were a product. Now, if we want to figure out what the value of delta H is here, we want to find the difference between the reactants and the products. So this quantity right here would be the delta H. So that's 60 minus 20, and it's going to be negative. Negative 40 because, again, we have an exothermic reaction, and exothermic reactions have negative delta H's. So finally, if we put a thermometer in this reaction, okay, here, okay, first of all, this is going to be endothermic. Okay, we have an endothermic reaction, and it is going to end up at a higher potential than the reactant. So we want to make sure that we understand what the surroundings and the system is. So the system is this reaction. So if we put a thermometer into the container, they're asking, would the temperature go up or down during the reaction? So here, this is endothermic. It would feel cold to the surroundings. Your thermometer is part of the surroundings. It would feel the cold, right? It would feel cold. The reaction would feel cold to it, okay? Because the reaction is absorbing energy away from the surroundings, including the thermometer. So it's taking heat away from the thermometer, so the temperature goes down, okay? Right? It is decreasing the temperature of the thermometer, okay? The thermometer measures temperature, the change in kinetic energy, okay? It is not measuring the potential energy. It is measuring how cold or how hot something gets. And in this case, an endothermic reaction will feel cold to the surroundings. All right, so a little bit more about delta H. Delta H is enthalpy. Enthalpy is another word for heat, basically. Enthalpy is basically the heat content, okay? Basically the heat that a system has. And I'll just mention this here, but at constant pressure, enthalpy is the internal energy. And there is a derivation in your textbook if you want to follow along to figure out how these relate to each other. Now, the important thing to understand is that we can't measure heat directly or enthalpy directly. We can only measure the change in enthalpy or the change in the heat. Okay, so delta H, again, just to drive this home, okay, delta H is positive for endothermic reactions, just like Q. Delta H is negative for exothermic reactions, just like Q. All right, so let's talk about this reaction. You can see there's a giant fireball that this guy is setting off. Okay, so we can only measure the change. And the change in the enthalpy change or the heat of reaction is the products minus the reactants. Okay, this is called, again, the enthalpy of reaction or the heat of reaction or the enthalpy change. I should add that to the slides. We can write something called a thermochemical equation for the production of water. That's what's happening here in this fireball. So thermochemical equation looks like this. It is a balanced chemical equation, but it includes the enthalpy change for that reaction as written. Okay, so we know that if this reaction happens as written, negative 483.6 kilojoules will be released. We know it's released because it's negative. It is important to understand that this release in energy, this 483.6 kilojoules, is released per 2 moles of water formed, okay, 2 moles of water produced, or 2 moles of hydrogen reacted, or 1 mole of oxygen reacted, or 1 mole of reaction taking place as written. Okay, so this number refers to all of these things, and which one you use will depend on the question asked. Okay, this is just like stoichiometry. This is the stoichiometry of the energy based on the mole ratios in the equation. So here's an example problem. We have hydrogen peroxide decomposing to water and oxygen by this reaction. And they are asking us to calculate the quantity of heat released when 5 grams of hydrogen peroxide decomposes. And here's the answer here. I'm going to show you how to do this, and then you should attempt the next 2 problems on your own. So let's see how this question is done. So here we have a thermochemical equation, and what they want us to calculate is the quantity of heat released. So right here, okay, so the quantity of heat when 5 grams of hydrogen peroxide decomposes at constant pressure. So we're given 5.00 grams. We want to find heat, which is Q. Okay, and they give us a amount of energy released for this equation, for the things in this equation. So remember here, this can mean several different things. It can mean minus 196 kilojoules per 2 moles of H2O2. It could also mean minus 196 kilojoules released for 2 moles of water produced. It could also mean 196 kilojoules per 1 mole O2, and it could mean 196 kilojoules for 1 mole of reaction. So it could mean all of these things, and we've got to figure out what we need to use based on the question that's being asked. So we're given 5 grams of H2O2, and we want to find heat, okay? And basically, that's going to be our kilojoules. So what I'm going to do is I'm going to basically take my 5 grams of H2O2, and I'm going to have to find a way to relate this to my equation and to my heat. So first off, right, in order to use this thermochemical equation, we need to change our 5 grams of H2O2 to moles. So first I'm going to convert my grams to moles by dividing by the molar mass. And then that will get rid of my grams, but now I need to relate moles to energy. So I take a look at the different things. I'm going to choose this as my conversion factor because that relates the moles of H2O2 to my kilojoules. So I'll put in minus 196 kilojoules per 2 moles of H2O2. So you can see that cancels out. And then when I multiply this out, I will get an answer of minus 14.4 kilojoules. And that is how much is released by the 5 grams of H2O2 decomposing. All right, so this next problem, part A, you should think about whether this is exothermic or endothermic. Well, I'm going to say it is endothermic because we have a positive delta H. Okay, we've got that positive sign there. And then go ahead and pause the video and try this yourself. See if you can take this thermochemical equation, read the question, and figure out how many grams of methane gas are produced. All right, now that you've had a chance to try it, we can see that we are trying to find, we're given 82.5 kilojoules. This is the energy or the heat. And we have to find the grams of methane. Okay, so we're going to start off with 82.5 kilojoules. And we need a way to relate kilojoules to, right, something in this reaction. So again, here we need to use our thermochemical equation. So I know that there are 258.52, excuse me, 0.8 kilojoules, okay, absorbed for every 2 moles of CH4. So I'm relating my kilojoules to my methane. So now if I look here, in order to get rid of my energy and change over to moles of methane, I'm going to put my 2 moles of methane on top and my energy on the bottom. So 252.8 kilojoules. That cancels out. And then I need to change my methane over to grams. So that would be 16.05 grams for 1 mole of methane. Okay, so when I multiply this out, I will end up with 10.5 grams of methane. So now we are going to look at this example, and it's back to stoichiometry. Stoichiometry never goes away. So here the question is asking how much heat. Okay, there's our question right here. How much heat is released when 4.5 grams of methane gas, methane is CH4, is burned with 8.00 grams of oxygen in a constant pressure system. Now notice right away, we've got 2 reactant amounts. All right, so we cannot make more heat, okay? The amount of heat is limited by the limiting reactant. Once that runs out, the reaction stops and you stop producing heat. So that's, again, an important idea, and it's directly related to limiting reagents. So the amount of heat produced, okay, so if you treat heat as a product, right, is just like any other product, it's limited by the limiting reactant. So we got to figure out which of these is the limiting reactant. Is it the 4.50 grams of methane, or is it the 8.00 grams of oxygen? So I'm going to convert both of those to moles. So 4.50 grams of methane, and I'm going to convert that to moles. And I get 0.280 moles of CH4 with my oxygen. I'm going to convert that to moles. And we have a molar mass of 32. Okay, and when we divide this out, we get 0.250 moles of O2. And we want to figure out which one of these is the limiting reactant. So let me convert my O2 to CH4, see how much is necessary to react this. So I know that 1 mole CH4, 2 moles O2. So this will give me 0.125 moles of CH4 to react the O2. And we've got excess of that, right? We've got much more than 0.125. So this is my excess, and my oxygen is my limiting reactant. So now I can take my limiting reactant here, okay, and use that to find the heat. Okay, so I can take my 0.250 moles of O2 and find the heat we get from the thermochemical equation, right? So it's minus 890 kilojoules for every 2 moles of oxygen. So I can multiply by minus 890 kilojoules for 2 moles of oxygen, and my moles of oxygen cancels, and I end up with minus 111 kilojoules released. So there's my energy released, my heat released. So then there were a couple demonstrations today. This one was very disappointing, I have to say. The MRE heater did not really heat up. But in this chemical reaction, we have magnesium powder, solid. When you mix it with water, you get magnesium hydroxide and hydrogen gas and a bunch of heat, enough to boil a liter of water without flames and smoke. And so here's my MRE. And so I added water. It's all cold now, but when I added it, it was usually it puffs up and you get a bunch of hydrogen gas being evolved very quickly, and it gets very hot. This only got mildly hot. So this is a exothermic reaction. Heat is being released. Okay, this is exothermic. And we can feel it getting hot because our hands are part of the surroundings. So we can feel the temperature increasing and giving off heat. And a thermometer measuring this would increase in heat, okay? Increase in kinetic energy, and the temperature would go up on a thermometer. On the other hand, if we have this next reaction, if we mix some barium hydroxide with ammonium cyanate, hopefully you can recognize that this is a double replacement. But this is a little bit of a special double replacement because when we put these together, we get NH4OH, but when I do this reaction out, I actually start smelling ammonia. So ammonia is this, okay? And the only way I can smell is if it becomes a gas and those gas particles reach my olfactory cells and I smell it. So we end up with ammonia, and what is happening here, this ammonium hydroxide is actually decomposing into ammonia and water. So we get some ammonia and water, as well as the other product of the double replacement. We get barium thiocyanate. That SCN ion is a thiocyanate ion, and water, of course, is liquid. So when I mix these two powders together, this is a white solid. You can see a slush forming, gets slushy. And the reason why it gets slushy is because you have water being released. The other thing is, usually I put this beaker on top of a piece of wood, a big piece of wood, and put some water in here, the reaction is so cold that it actually freezes the beaker to the wood, freezes the water under the beaker, and then the beaker gets stuck to the piece of wood, and I can actually pick up this huge piece of wood with my beaker, and it gets very, very cold. So this is an example of an endothermic reaction. If you had a thermometer in here, the thermometer's temperature would go down. Okay, you would see a decrease in the temperature because the reaction starts absorbing heat away from the thermometer. The glass absorbs heat from the beaker, from your hand if you hold it, from the wood, and all of that serves to slow down the kinetic energy, the average kinetic energy of the surroundings, and the temperature goes down, okay? So this is an endothermic reaction. The temperature goes down and it feels cold. I will link in a link to this demonstration, a video of this demonstration, because it's one of my favorites. It's just so cold. It's so cool. All right, so in both of those demonstrations, heat is being moved and manifested as a temperature change, okay? We can see the heat transfer through a temperature change. How do we quantify this and measure the heat transfer? So this is through temperature, okay? But we want to first understand why this heat transfer happens, okay? Why is it that we end up with heat going from a hotter object to a colder object? So here, right here, let me go to the other slide so that you can see this animation. So now you can see this little animation here. You can see that heat transfer happens through collisions between particles. So if you have something with low kinetic energy, okay, low temperature, okay, that means that if something with higher kinetic energy, a higher temperature, higher average temperature, a particle collides with a particle with lower kinetic energy, some of that energy gets transferred, okay? And this molecules keep on colliding and transferring energy until that energy spreads out across the whole system, okay, across the whole combined system. This is a natural tendency in nature, in the universe, that if you have an area of high energy, high temperature, large kinetic average kinetic energy, and then you bring it together with a substance or a material or some object which has lower kinetic energy and lower temperature, the heat, the kinetic energy will spread out so that each of those objects at the end will have the same average kinetic energy. So here again, you can see that, right, if you put a colder object or a colder container of water in a hotter container of water, eventually, okay, you've all observed this, the temperatures stabilize, they stop changing, and you reach something called thermal equilibrium. And at that point, the average kinetic energy of those particles and the temperature is the same. So here, another illustration of this, two blocks, one hot, one cold. They each have their temperatures, okay? The hot one has more kinetic energy, a higher temperature. Cold one has a lower kinetic energy, lower temperature, but then you make them touch, heat starts transferring through the vibrations of the atoms in the hot block, and they transfer over as they touch and vibrate each other. The kinetic energy gets transferred over to the cooler block, and so on until heat stops transferring. Okay, so when they reach the same temperature, when the temperature stops changing, they have reached thermal equilibrium. There's no more heat transfer going on. Here's another example of conduction through a mug. So if this is the coffee and this is the walls of the mug and here is the surrounding air, we can see collisions with the solid in the mug causing changes in the vibrations of these atoms or increasing them, right? Transferring kinetic energy to the mug, and then further transferring the kinetic energy that is gained by the mug into the colliding air particles, the air molecules and atoms here. So eventually the heat will conduct from the coffee out into the surrounding air until everything is the same temperature. And we've all experienced this. If we have a hot mug of liquid, but we leave it over time, right, the mug becomes the same temperature as the surrounding air, as the room. There are two other ways that heat can be transferred through convection, which is fluid motion, okay, the motion of fluids carrying particles with higher kinetic energy to areas with lower kinetic energy. You may have heard the term heat rises, and so this is a form of convection. And then the other form is radiation, through emitting electromagnetic radiation, through emitting light, basically in the form of infrared radiation. So infrared radiation is heat in the form of waves, so heat in the form of light energy. So that can be radiated off, and there is no collision going on there between molecules. That's just being emitted through the emission of light. So keep in mind, temperature and heat are not the same thing, okay? Temperature is a measure of the kinetic energy. It relates to the speed of the molecules. It measures how hot or cold something is and tells us how the heat will flow, okay, from the colder thing, from the hotter thing to the colder thing. And we measure it in degrees Celsius, Kelvin, or Fahrenheit. We're just going to use Celsius and Kelvin. So heat's always going to flow from the hotter thing to the colder thing because the kinetic energy will be transferred, okay, from an area of higher kinetic energy to an area of lower kinetic energy until the collisions are transferring the energy and spreading it out so that the heat no longer gets transferred and the temperature stops changing. Heat is the exchange of thermal energy, okay, that is caused by temperature difference. Okay, so we can only see this when it is changing or transferred. And it's measured in joules or calories or BTUs, which are British thermal units. All right, so a couple more Pear Deck questions. So if we put this beaker water in here, and we did a different experiment where we put X into here, asks which beaker would result in the higher temperature, and that would be Y, right? There's more mass of water in Y. It's almost at the same temperature as X, and so it will transfer more heat, resulting in a higher temperature of these two combined. Which beaker water transferred more heat? Well, I just answered that. Y is going to transfer more heat. The final temperature of Y plus this beaker will be greater. So keep in mind that when we transfer heat, it's caused by both the starting temperatures, the mass of the material affects it. I should also say that it depends on the material. Okay, so different materials have different heat capacities, which we're going to look at in a second. Okay, so now if we have equal quantities of hot and cold water in a perfectly insulated container, okay, and we mix them together, the final temperature of the mixture is going to be exactly in the middle. Okay, exactly in the middle between the two temperatures. So what do I mean by this? So if we start out with 100 degrees C and we go to 50 degrees, okay, for the cold water, they are going to meet at 75 degrees, just exactly in the middle. And that will be the thermal equilibrium point, that temperature. Okay, here we end up with an equal temperature for all of the water. If we mix more cold water with less hot water in a container, so we got a lot of cold water, a small amount of hot water, then the final temperature of the mixture has to be closer to the cold temperature. Okay, not in the middle, right? Because, right, right, we've got less hot water, right, and the temperature that it ends up at is going to matter depending on the mass of the water as well, not just the temperatures that they're at. So the temperature is all the same at thermal equilibrium, and we need to assume that the heat lost by the hot water is equal to the heat gained by the cold water. So another example of this is if my mother-in-law comes to swim and says the pool is cold, I say, oh, let me go get you a tea kettle of water. And I get her a kettle of boiling water and she pours it into the pool. Well, guess what? They're going to reach thermal equilibrium. The kettle's going to transfer some heat into the pool. However, right, they're going to not, okay, the pool is still going to be cold, right? The pool has a much greater heat capacity. There's much more pool water, cold pool water than the tea kettle water. So even though they reach thermal equilibrium and they reach, okay, right, they reach the same temperature, right? That temperature is going to be very close to the temperature of the cold pool water because, right, the tea kettle has hardly any heat capacity because the amount of water is too small. All right, so now how do we actually measure this heat transfer? How do we actually calculate it for different processes? So we use something called calorimetry. That's the actual science of measuring the heat transfer. And a calorimeter is the device that we use to do calorimetry. So it measures the temperature before and after a physical or chemical process. So the kind of calorimeter that we will use mostly is the one on the left, a constant pressure coffee cup calorimeter. Looks like this, okay? And in your lab kit, you have some styrofoam cups, or you may have a paper coffee cup, but it has a thermometer in it to measure temperatures. It might have a stirring device to stir the reaction as it's going along and make sure things get distributed well. And it might have a lid. You probably don't have a lid. I don't have a lid on this, but it is used to measure the heat that is gained or lost by a reaction by measuring the temperature before and after. And there is an equation to relate the temperatures to the heat. The calorimeter on the right, we are not going to be using. We don't have a bomb calorimeter. Okay, but this is basically how people figure out the energy content of different foods or fuels or materials. So this little container right here is called the bomb. And in the bomb, there is like a cup where you put your sample. There are wires going into the sample. And this is closed off and it's surrounded by water and insulation so that heat is not lost, or at least not too much heat. And basically you set off, you ignite the sample, okay, by applying electricity to these wires, and then it explodes and combusts the sample. And as the sample combusts, it gives off heat, which is released and absorbed by the water. Okay, so the sample releases heat as it combusts. That heat gets transferred out the bomb and gets absorbed by the surrounding water. So the thermometer picks up the increase in kinetic energy in the water after the bomb combusts the sample. And it measures this temperature change in the water due to the release of energy from the bomb. So again here, I think I mentioned this already, but we are going to deal with the constant pressure, the coffee cup calorimeter, rather than the bomb calorimeter. We may see some examples of that, but most of our problems are going to focus on the coffee cup calorimeter, the constant pressure calorimeter. So we've got a bunch of different ways to talk about heat capacity. And first of all, heat capacity is the amount of energy required to raise the temperature of an object by 1 degree C. So here, this big capital C stands for heat capacity. That's the heat, Q, divided by the change in temperature. The molar heat capacity is the heat capacity of 1 mole of a substance. So if you take the heat capacity and you divide it by the number of moles of the substance, you get C sub m. That's the heat divided by the moles divided by the change in temperature. So it has units of joules per mole degree C. And you can see that the Q, the heat, is equal to moles times the molar heat capacity times delta T, where N is moles. And then the specific heat, little c, is the heat capacity of 1 gram of a substance. So here you can see that the units are joules per gram degrees Celsius. And then Q is the grams of substance times the specific heat times delta T. So that's Q equals MC delta T. All right, and it turns out water has a specific heat of 4.184 joules per gram degree C. And in calories, it's very simple. It's the specific heat of water is just one calorie per gram degree C. Okay, so just a little bit more about the specific heat capacity, little c, lowercase c. You do not have to memorize these values. Okay, they will always be given to you. And the specific heat of water will be given to you. I'm not sure why this is 4.186. It should be 4.184. But this equation is on your formula sheet right here, okay, under thermodynamics and electrochem. And so you have the Q equals MCAT equation, and they give you what the variables mean on the right-hand side. So here's a practice problem. Go through using Q equals MCAT. All right, so this practice problem asks for how many joules of heat. Okay, so joules of heat, that's going to be our Q. We'll raise the temperature of exactly 50 grams of water. So that's going to be our mass at 25 degrees C to 75 degrees C. So we're going to get some delta T from this, right? So if we take 75 minus 25, we will get delta T as 50 degrees C. And then C, the specific heat of water, is right here. We can put that in for C. This is basically a plug and chug. So Q, the heat, is equal to 50 grams times 4.184 joules per gram degree C. Okay, times delta T, which is 50 degrees C. And you can see the units canceling out nicely. And if they don't, then maybe you should look at your numbers again and figure out what went wrong. But once we multiply these things out, we'll get a value of, let me get this value in here, get 10,460 joules. Okay, so there's our amount of joules necessary to raise the water by 50 degrees C. Okay, so our water, if that's the amount of heat that we have to put into the solution, that heat had to come from somewhere, okay? Just keep that in mind, okay? That heat that was put in was provided, that same amount of heat was provided by some other substance or the surroundings. Here, the molar heat capacity for water, if we start off with the specific heat of water, 4.184 joules per gram degree C, if we multiply by the molar mass of water, 18.02 grams per mole, we will get the molar heat capacity because the grams cancel out, and we will get 75.40 joules per mole degree C, and there's our molar heat capacity. So also just keep in mind that we also have just plain heat capacity. So big C, okay, is just the heat capacity of water, or the heat capacity. And for water, it's going to be 4.184 joules per degree C, or in calories, it is 1 calorie per degree C. All right, so let's do another practice with MCAT. Q equals MCAT. So again, here we've got the amount of energy required to change temperature of 36 grams of water from 5 degrees C to 65 degrees C. And I don't know why there's a line under that degree sign. Also, this should be 4, not 6. So if we, again, plug these numbers into Q equals MCAT, this 36 is our mass. Our specific heat is 4.184. And then our delta T is going to be 65.0 minus 5.0. So we will get 60.0 degrees Celsius. And that goes into delta T. So I've got this set up on the next page. Okay, so you can see Q is the mass times the specific heat times delta T. Let me just make sure this is 4. So if we multiply these things out, we will end up with 9,041.76 joules, but with sig figs, it'll be 9.04 kilojoules, or 9,040 joules. All right, so now there's this problem. If you're going camping and you got the choice of bringing in a gallon jug of water or a big rock of equal size, both reaching a temperature of 75 degrees C, which one of these would you bring into your sleeping bag to keep you warm throughout the night? The water jug or the rock? Well, it turns out it's the water jug. Okay, water has a pretty high specific heat capacity for its molar mass. And so as it cools, it's going to release more energy per gram per degree as it cools down. Okay, so as it loses 1 degree of temperature, it will release more energy because it had to absorb more energy in order to be raised 1 degree. Now, we discussed in class how it is not necessarily intuitive that water would have a higher specific heat than a rock. So this next problem, actually, if you take a look at these large rocks, the specific heat of the rock, these rocks, is 0.82 joules per gram Kelvin. It's actually significantly smaller than water. Okay, water has a specific heat of 4.184, and rocks have a specific heat about, it varies, but 0.8, 1. So I don't think that's necessarily intuitive or, obvious that that would be the case. So in this problem, we're going to figure out how much energy is necessary to bring, it says, quantity of heat absorbed by 50 kilograms of rocks if their temperature, bring it up 12 degrees. If you're going to bring their temperature up 12 degrees, how much heat do these rocks have to absorb from the sun, okay, to store the heat? So here we're going to use, again, our Q equals MCAT equation for A. And Q is our unknown. Calculate the quantity of heat. Our mass is 50.0 kilograms. Now, let's look at the units that we need here. All the units we need are in the specific heat. So we need joules, grams, and kelvins. So here we have kilograms. So I'm going to change that over to grams because I want it to cancel out in my specific heat. So 1,000 grams for 1 kilogram. So my mass is going to be 50,000 grams for the rocks. My specific heat is given right here. So C is 0.82 joules per gram. They're using Kelvin here. And then my delta T, remember that an increase of 12 degrees C is the same as 12.0 Kelvin. Okay, the change for Celsius is the same as the change for Kelvin. All right, so now we just need to plug and chug this in. So Q equals 50,000 grams times my specific heat, 0.82 joules per gram per Kelvin, and then 12 Kelvin. And then I multiply this out, and I get 4.9 times 10 to the 5th joules. Okay, and there's our answer right there. So that's part A, okay, the amount of heat necessary to raise the temperature 12 degrees. In part B, it says, what temperature change would these rocks undergo if they emitted this much heat? Okay, so I like to underline things and label, so that's my Q. And what temperature change? That's a big clue that my delta T is my unknown here. But I'm going to use Q equals MCAT again. This time, I need to solve for my delta T, right? Because we want to find the delta T. So I'm going to solve for delta T. So delta T is equal to Q over MC. I've got my Q. I have my mass. I have my specific heat. I can solve for the temperature change that would happen if the rocks emitted 450 kilojoules of heat. Now, I just want to check my units again. I see that I need joules, so I'm going to convert my 450 kilojoules to joules by multiplying by 1,000 joules per kilojoule, and I will get 450,000 joules. Okay, let's get the right unit on there. So let me plug this in now. 450,000 joules divided by my mass of 50,000 grams and divided by my heat capacity, 0.82 joules per gram Kelvin. And let's just make sure everything cancels out and we're getting the right unit. We're going to get Kelvin here. So when I solve for delta T, I get 11 Kelvin, okay, decrease in temperature. Okay, so rocks will go down by 11 Kelvin if they release this many joules of heat. All right, then we actually did not do this problem in class. So, and we actually skipped it and went to 5.50, where we have two solid objects. We got A and B. So A and B, and these are placed in boiling water and allowed to come to temperature there. So A and B, let's just make them little cubes things. They're both at 100 degrees C initially. Okay. And then we have a container of 1,000 grams of water at 10 degrees C. Okay, so initially, that's what we have. We then plunge the object A into the water, and they reach thermal equilibrium. Okay, so A is now in the water, and at thermal equilibrium, it says that object A increases the water temperature by 3.50 degrees C. So at the end, it's 13.50 degrees C. Okay, everything is at that temperature. All right, so that's object A. B, same thing. We put it in exactly the same amount of water, so 1,000 grams of water at 10.0 degrees C. And then we plunge B in and we allow it to reach thermal equilibrium. Okay, so B is in here. All right, and for B, the final temperature is 12.6 degrees C. So the question is, which object has the larger heat capacity? All right, so we can think about this like just in terms of, terms of what happens with the temperature at thermal equilibrium. A raises the temperature of the water more than B. Okay, so it must be releasing more energy into the water. Okay, because it gained more energy when it was being heated up. So A has a larger heat capacity. Now, what if, it's always nice to have some kind of quantitative backup. So another way to look at this is if we have the Q gained by the water is equal to the Q lost by A. Okay, that has to be true, right? The amount of heat gained by the water must have come from the hot piece of A. So here we can do this in terms of heat capacities. So C, H2O, this is big C because it's heat capacity, times delta T water equals C A times delta T A. Okay, and if we look at that equation, we know this big C is 4.184 joules per degree C. The change in the water temperature, okay, is 3.5 degrees C. That equals the heat capacity of A, which we don't know, and delta T for A goes from 100 minus 13.5, so that's 86.5 degrees C. Okay, so we can solve for some heat capacity here for A. Same with B, we can set this up 4.184 joules per degree C times 2.60 degrees C is equal to heat capacity of B times, in this case, it's going from 100 to 12.60, so that's 87.4 degrees C. So comparing at these numbers, right, this is a smaller number divided by a larger number, and this is a larger number divided by a smaller number. C of A, right, heat capacity of A is going to be a larger number. It has to be than heat capacity of B. So again, that's due to the fact that when we heated up A, it required more energy, Okay, more energy to heat A up to 100 degrees C. It had a larger heat capacity. Okay, so finally, this is an important note, very important. Q is not the same as the heat of reaction. Okay, Q, the heat, is not the same as delta H. Q is just the energy released or absorbed by a process, and the units are going to be energy units, joules, calories, ergs, BTUs, whatever. Okay, but delta H is the energy released or absorbed for 1 mole of reaction. So this is going to have units of energy per mole reaction. So on Thursday, we will look at how this applies in calorimetry. And one of the problems in your homework, we'll see if you guys get that distinction there. But if not, we will go over it and make sure everybody's in the same place.